Welcome everyone to today's webinar on system-dependent factors influencing shear wave speed measurements for liver fibrosis characterization, presented by Dr. Mark Palmeri. After today's presentation, participants will be able to describe shear wave generation and methods to ultrasonically estimate their speed. Viewers should also be able to describe how the stiffness of tissue can be represented and review the latest QIBA recommendations to improve intermanufacturer system consistency. The AIUM is accredited by the ACCME. This webinar is designated for 1 AMA PRA Category 1 credit. Credits for this webinar are approved for physicians, sonographers, and radiologic technologists. Participants who complete the post-test with a grade of 70% or higher will be awarded 1 CME credit. As an ACCME accredited provider, it is the AIUM's policy to ensure that the contents and quality of this educational activity are balanced, independent, objective, and scientifically rigorous. All individuals who are in a position to control the content of an educational activity are required to complete a disclosure form. All disclosures are reviewed by the AIUM, and any conflicts of interest are resolved or managed prior to an activity. Dr. Palmeri receives technical and in-kind support from Siemens. Disclosures for AIUM staff members and individuals involved with planning this activity were provided in the email you received. During today's presentation, if you have questions for the presenter, you may submit them by typing them into the question box on the right side of your screen. You will be able to submit questions throughout this webinar, but the presenter will not begin answering until the end of the presentation, at which time he will answer as many questions as possible. A recording of this webinar will be available on the AIUM website. And now, we're pleased to present Dr. Mark Palmeri.
Thank you, Kathy, for that introduction. I'm excited to be talking about this topic today. It's been a topic near and dear to my heart for many years, and one that has actually been, I think, a nice success story for technology translating from the research environment to being commercialized relatively rapidly. So we'll be talking today about system-dependent factors that influence shear wave speed measurements for liver fibrosis characterization. As was discussed already, my disclosures have been made known, and specifically we do work closely here at Duke with Siemens Medical Solutions. I won't go through all of the objectives in detail since they've already been written out, but the hope of today's talk is to really give you a background of the physics involved with using acoustic radiation force to generate shear waves, some of the way that those propagating shear waves can be used to characterize tissue properties, and why those tissue properties might correlate with certain disease states, in this case liver fibrosis. Really discuss some of the early generation assumptions that have been made in shear wave speed measurements and how those are being refined to more accurately capture all of the properties of actual tissue, and then look at some of the latest efforts that are being tackled to try to standardize these measurements, both in terms of the protocol for clinical execution and to standardize some of the consistency between different manufacturer-based systems. So as a general outline, we'll cover some of the background material right off the bat, hopefully have a common language and understanding of how these systems work, quickly review the motivation for characterizing liver fibrosis this way, do an overview of the RSNA QIBA effort that's been focusing on standardizing shear wave speed measurements, including a teaser with how we're comparing that with another modality that characterizes tissue stiffness, which is magnetic resonance elastography. Do a really brief overview of the active profile recommendations that are in process, and then wrap up today with some conclusions. So one of the first questions someone might have is why image tissue stiffness. For ultrasound, historically, material properties haven't been a reported metric. Everyone looks at echogenicity or flow parameters with Doppler and things along those lines. But we do know that clinically tissue stiffness already has great traction among the practitioner. We know that manual palpation is a common way for people to try to delineate things about disease state, palpation of things like breast masses, the digital rectal exam, feeling nodules throughout the body. But we also know that the practitioner's ability to palpate things has limitations, primarily physical location of where that structure might be, the size of the structure, and of course there's challenges when trying to record information gleaned from palpation. So how does one doctor characterize something hard versus another doctor? How do you report that information for longitudinal monitoring or looking for changes over time? So there's kind of a natural motivation here in the clinical space to characterize tissue stiffness and to have a reliable way to record that. And just to get some definitions for common nomenclature to be used, hardness and stiffness are commonly used interchangeably in the literature. They do have actually a slightly different formal materials definition, but for the sake of what we'll be referring to or what you would come across in the literature, stiffness is just the resistance of a material to some form of deflection or deformation. So if you press with a uniform amount on a given piece of tissue, the more that it resists deforming in response to that push, the stiffer it would be. Softness, of course, is the inverse of that and is looking at the compliance of the material. As a clinician, very few clinicians are able to come up with absolute stiffnesses on the fly after palpating something. So most clinicians are looking actually at stiffness relative to adjacent tissues, where the adjacent tissues are things that are easier to compare across patients, so potentially muscle or fat stiffness or something like that. And typically the clinician is gleaning other information other than just relative stiffness. They're also characterizing things about the boundaries of the structure. Is it tethered? Is it mobile? Does it roll under your finger? What does that surface texture feel like? And these are various characteristics we might want to be able to capture in an elasticity imaging system. To give some context of why there's also motivation from just a characterization standpoint, the stiffness of a material can be characterized by its Young's or its shear modulus. And typically in the literature, those are represented with the variables E for Young's modulus and a mu for shear modulus. And what I've listed in the table that you can see here is actually for a variety of types of tissues and disease states of tissues. You can see there's a pretty large dynamic range for how much that modulus might change. So for example, something like fat could have a nominal Young's modulus of 1 kilopascal, where kilopascal is the common unit this is reported in, whereas something like myocardium in the heart could range from 20 to 150 kilopascals. Now I want to contrast that with some of the typical material properties that an ultrasound system, B-mode imaging system, would take advantage of to make a picture, which would be the bulk modulus of the material or the dilatational wave speed, or effectively the compressivity of the tissue. And if you look at that, you'll see that the bulk modulus and dilatational wave speeds for all of these tissues and all these different disease states are all in the same ballpark and order of magnitude of each other. So by moving to things that are more characterized by things like our Young's and shear modulus, we're actually expanding the dynamic range of how we can resolve different tissue types and disease states. And that gives us potentially a greater mechanism and foundation by which we could have contrast to delineate these different things from one another. What you'll quickly see in the literature too is also reported shear wave speeds. And the expression at the bottom of this slide relates the three of these parameters together, and we're going to go over that in a little more detail. So I dedicated an entire slide here to how we compare elasticity metrics because they're reported in different ways in the literature, even though all are making usually the same assumptions for reconstructing these properties. So the typical assumptions that are applied to soft tissue are that the tissue is elastic, and we'll go into more detail in a little bit as to what constitutes an elastic response. A big one is that we consider the tissue incompressible. So we assume that water dominates the primary constituent of a lot of these things and that its overall volume is maintained under deformation. And we assume that the tissue is homogeneous and isotropic. So we assume that it's the same everywhere that we're characterizing it and that it's independent of the orientation by which we characterize it. You could, of course, imagine that if you're looking at tissues such as connective tissue, muscle, things like that, that suddenly the isotropic assumption and the homogeneous assumption might be violated, and you'd be correct in thinking that. But these are common assumptions that are applied. Under these assumptions, we can relate the Young's to the shear modulus by a simple factor of 3, and that's primarily, again, assuming that the tissue is incompressible. That is one of the primary determinants of that factor of 3. And then you could also relate this to the shear wave speed, which is delineated as C sub t for transverse wave speed. C sub t can be related to those elastic moduli, but one key note here is that there is a power of 2 relating the elastic moduli to the speed. So if you're looking in the literature and drawing comparisons between them, it's not fair to say that you could just kind of linearly scale everything and be able to come up with similar thresholds or ratios of parameters. Shear wave speed actually has a quadratic dependence relative to the elastic moduli under these assumptions. To give you some feeling of what different systems report, I've listed some of the more common systems that are on the market. This is not completely comprehensive. Young's modulus has a lot of traction for the supersonic Imagine Explorer system that's on the market, and another common system used that uses that metric is the EchoSense FibroScan. Shear wave speed is a metric reported by systems from GE, Philips, Siemens, Toshiba, Samsung, Zenari. And shear modulus is actually a metric reported by some of the magnetic resonance elastography systems. So you can see how under the same assumptions for characterizing the same type of tissues, it really makes the reader or the user have to do a little bit of conversion to crosstalk between these. So jumping over more specifically to what the ultrasonic shear wave speed systems do, to generate that deformation that we said a clinician would do potentially with their hand through manual palpation, we instead will utilize acoustic radiation force to generate the deformation. An acoustic radiation force is generated in the same exact acoustic footprint that a focused B-mode or Doppler pulse would go in, but typically we use slightly longer pulses to be able to generate measurable displacements in the tissue. So that longer pulse could be on the order of several hundred cycles of insonification, which is typically tens to hundreds of microseconds of on time. All the existing systems on the market remain within current FDA acoustic output limits. And you will notice that the force profile, which I'm showing on the left of this slide, has a dependency on several things. One thing you'll notice is a dependency on the focal gain. So if I'm focusing at a certain depth, I'm not actually pushing with a uniform force the entire distance from transducer to focus, but there's actually a gradient there in the push. And that allows us to get excitations at deeper locations with adequate SNR. The radiation force magnitude is also dependent on the acoustic attenuation, which is the alpha term in the expression above it. And it is also determined by the sound speed, which is again a function of our bulk modulus and density. So the big ones here would be the focal gain, and the acoustic attenuation can really primarily modify the distribution of that radiation force sum. For shear wave elasticity imaging, the animation on the left is actually showing the displacement fields that would be generated from a radiation force excitation that was just shown on the previous slide. And similar to dropping a pebble on a surface of water and watching the waves emanate out from where that pebble was dropped, the shear waves that are generated from an acoustic radiation force excitation also propagate out and away from where that radiation force was applied. And what we can do to track how fast that wave is traveling is by looking at a multitude of spatial locations that are spatially offset from where the excitation was applied. And that's shown in the right-hand figure by the 3 different arrows. And it's typically more than 3 locations, but this is just for demonstration purposes. And what you can see is that immediately after the excitation is applied, which is labeled as the 0 millisecond, we just have deformation where we applied the radiation force, and as we look later in time, we see the wavefront spreading across. And if we track at those different locations the time at which the wave arrives, we now have a mechanism to correlate arrival time to spatial position. This is showing again that we could look at these arrival times at different spatial locations at a multitude of depths So in this case, if we're applying the radiation force at a lateral position of -2 millimeters in this animation, and we track at different spatially offset beams from that and look at 3 different depths, we see that at the different depths we can characterize the arrival time, and as we move farther and farther away from that excitation, the arrival time as we expect would occur later and later. So if we look at how we can then actually reconstruct the speed from that, the top left plot here is showing in a soft medium what the displacement profiles through time look like at different spatially offset positions. The dashed yellow would be where the excitation was applied, and then going at several spatial increments up to 2 millimeters offset, you can see that there's offset arrival times at those different spatial locations. If we look at a stiffer medium, shown in the bottom left plot there, you can see that for the same spatially offset locations, you see faster arrival times for each position. And if we make a plot, for example, of arrival time or time to peak, which is what TTP stands for, as a function of the lateral position, we can see in these elastic materials that we get a linear slope, and the shear wave speed is simply just the inverse slope of the arrival time versus the lateral position. So that gives us one mechanism by which we could reconstruct shear wave speed using a simple arrival time metric at different lateral positions. It's worth noting that time to peak is just the method that I'm graphically showing here. Different methods exist using things like correlation-based approaches or using more high-order mechanisms to estimate this arrival time, but the general premise of it can be captured through this simple representation. Okay, so now let's move over to the clinical application that's had the most attention for shear wave imaging, which has been the liver biopsy. So liver biopsy, I think, as most people know, is the gold standard right now for characterizing concerns for liver fibrosis, and the disease etiologies at play there tend to be viral or alcoholic, infectious in the sort. The problem, of course, with liver biopsy is that it's invasive, has a risk of infection and hemorrhage and pain. Hemorrhage can be a real concern because in the case of liver dysfunction, you could also have compromised clotting abilities. Of course, you're also taking usually a single needle core of a very large organ, so you have limited sampling. Because you have post-procedural monitoring times and processing here, it can be costly to do. And because of all this overhead, it's not very suitable for longitudinal monitoring or progression of disease or response to treatment. So this was a natural match potentially for looking at shear wave speed metrics to potentially complement or replace liver biopsy, where the mechanism of stiffening with the fibrotic deposition might be something that we're sensitive to. Just as a little teaser as to what the underlying pathology is here, this is just showing some examples of healthy liver where the normal microanatomy is really a complex network of sinusoids that allows blood to be filtered and allows different constituents to go in and out of the blood from the liver itself. In the case of liver fibrosis, what happens is that we start to get a scarring happening around some of those conduits for blood flow, and the different stages of fibrosis, typically characterized by the METAVIR score, really are alluding to the morphology of that fibrosis. So as the fibrosis starts to form around discrete islands and then starts to bridge across and coalesce, that is what corresponds to increasing stage of fibrosis and disease. And we're hoping that shear wave speeds are going to be sensitive to this extent of fibrotic change in the liver. Like I mentioned before, there are a variety of commercial systems on the market that have been exploring this, first in the research literature, looking at both radiation force systems and some other systems like the FibroScan, which doesn't actually use radiation force but uses a mechanical punch from the skin. People have looked at reporting just a single number back from a region of interest, similar to what the Siemens system on the top shows. The supersonic system, the Explorer system, can actually early on was showing 2D regions of interest with shear wave speeds, and multiple systems now offer that. And one of the interesting things that has come from systems becoming available to clinicians is that while there's similar trends as shown on the left of increasing shear modulus or shear wave speed or Young's modulus with fibrosis stage, there's some challenges in finding thresholds of speed or modulus that correspond to a specific fibrosis stage, or having multiple systems report slightly different numbers when imaging the same patient. So that variability between systems and kind of the clinician's need for having a robust measurement modality for looking at liver fibrosis is what catalyzed the RSNA QIBA effort. And so the Quantitative Imaging Biomarker Alliance was formed through RSNA back in 2008, and it really was looking at extending what were traditionally imaging systems into quantitative measurement systems. And the objective of QIBA overall is to come up with protocols and profiles that have specific claims about what a measurement system can do. The ultrasound group had its own committee formed in 2012, and shear wave speed estimation for liver fibrosis was chosen as the first quantitative metric for ultrasound. And one of the primary tasks of the committee was to understand the bias and variance between these different shear wave speed imaging systems that were starting to show up on the market. Additional clinical motivation, in addition to what I've already alluded to, is that there was a need for the different clinical bodies out there to start putting out guidelines on how to use shear wave speed. So a variety of organizations started to put out clinical recommendations and consensus statements, and that further supported the need for the QIBA group to really come up with some common language and protocol for the different manufacturers and end users to try to adhere to. And we also needed to figure out if we had an opportunity to provide some sort of controlled data sets or protocols for people even to use in-house to verify whether or not a system was behaving as it was expected to once deployed clinically. I'm just showing one example plot here, some of the meta-analyses that have shown up in the literature, again to highlight the need of standardizing to reduce variability. This is showing data from a meta-analysis that's cited at the bottom of the slide here, showing the probability of existing in a certain METAVIR fibrosis state given shear wave speed measured by a given system. And of course, ideally we would have nice discrete curves associated with each fibrosis stage such that speed could clearly and uniquely delineate each different pathologic state very clearly, but what you can see from the meta-analysis is that there's actually a decent amount of overlap between how speed correlates with fibrosis stage. And that's especially true at some of the intermediate stages, specifically the F2, F3, which is where we also clinically might be most interested in making different treatment decisions. So the hope here is to come up with some ways that we can, from a systematic standpoint, tighten up these distributions. There were a wide list and array of system variables that could have been at play when we very first started this effort. One that I'll come back to, and the first one that I actually delineate here, is the fact that the focal configurations that people use to generate their radiation force, both at a given focal depth and potentially at different depths throughout the liver and positions, could have different shapes and morphologies. And that actually leads to different frequency content of the resulting shear waves. And by different frequency content, you could think of that as the shape, how steep the rising edge is, and the general temporal profile could be different between systems. And we know that tissue, even though we've assumed it to be elastic, could actually be sensitive to those changes in shear wave morphology. And tissues that are dependent on the rate at which that shear wave comes through would be known as viscoelastic. So they have some dependence on the rate at which they get excited and deformed. And we know that higher frequencies or faster rates of change would lead to higher reconstructed shear wave speeds. So that was one of our identified potential confounding factors. We also know that shear waves could encounter structures and be reflected back into our regions of interest. We know that there's limitations on how finely sampled spatially and temporally shear waves can be reconstructed. And there was also potential protocol variability in the number of measurements used, where they were taken, how outliers were dealt with. All of this gave us a potpourri of topics to investigate. And we're going to really focus a lot on that first one of the viscoelastic assumption and the frequency content of shear waves as what we thought might be a primary confounder we could address. So we've conducted so far since 2012 2 phases of tissue mimicking phantom studies to try to get at the question of whether or not viscosity was a primary confounder in these measurements. And we started a phase 1 study by looking at 2 tissue mimicking phantoms that were closely assumed to be purely elastic, meaning that they should not have any of that frequency dependence. And we chose 2 nominal shear wave speed phantoms to distribute to different manufacturers, one that was at 1 meter per second nominally and one that is at 2 meter per second. In parallel to that, and I won't discuss it too much, we also came up with some digital tissue mimicking phantoms using numerical simulation tools, and those are also made available to the community to download and test things like reconstruction algorithms and the sort. For this first phase study, what we did is we actually manufactured CIRS, who makes a lot of ultrasonic tissue mimicking phantoms, made replicates of all of the 1 and 2 meter per second phantoms such that a unique pair could be sent to each imaging location. What we had to quickly calibrate was how much manufacturing variability existed between all those replicated phantoms. And what the plot on the left is showing is some measurements that we did at Duke on all of these replicate phantoms to see how much variability existed. Most of the variability was between 5 to 7%. And because we measured all of the phantoms at the same site with the same system, the plot on the right is showing how we were able to adjust all of the phantoms so that they had not only the same speed that we could do for cross comparisons between all the systems and sites. What this next plot that I'm showing is demonstrating here is how the different systems compared in measuring these pairs of phantoms. So as part of the QIBA effort, when we're doing these sort of comparative studies, we actually purposely withhold all of the manufacturer and system information since we don't want to necessarily highlight one system's performance over the other. So what you're seeing on the x-axis there with all of those different labels are effectively different systems at different sites. And then you're seeing each of the data in pairs with both what should be the 1 and the 2 meter per second phantom. So if you look across, for example, at 1 meter per second, the distributions of the box plots and their relative positions to each other would show you the system variability that existed in that phantom, which is close to what a healthy liver would be. On the top, looking at the 2 meter per second projection, you could see greater variance, which is expected in general with systems, and some greater offsets there. And looking at the table below, you're seeing an ANCOVA analysis that obviously shows that stiffness is the primary degree of freedom that leads to differences in these data. But you could see actually that system wasn't necessarily our second-ranked confounder, but it actually was focal depth. And that is something I'm going to delineate in more detail on the next few slides. So what we wanted to do was look at some of the system data in aggregate. So what I showed on the previous slide was individual systems at various sites. Several sites shared the same type of system being used, and we assumed that we could combine that system data if it was using the same software version and transducers and the sort. And again, there's no x-axis for these box distributions because they're not detailing which system was which. But what you can notice is the horizontal line there is kind of showing the grand median across all of our data. You're seeing how much then a given system aggregated across all of its sites, how it compared to that grand median, and on average some of the distributions deviated by about 12%. You're also seeing data that was acquired on research systems at Duke and the Mayo Clinic. That's shown there as Verisonics Duke and Mayo there as comparative distributions. And now we're starting to get a quantitative feel for how much these systems varied from one another in these elastic phantoms. Please keep in mind that these data included 3 different focal depths that were being measured, 3, 4.5, and 7 centimeters. And as I'll show you in a bit, that focal depth variability was actually potentially one of the primary confounders. These data I'm showing here are for the soft phantom. If I switch to the stiff phantom here, you'll actually see that while the absolute variability between the systems from the grand median is about the same, it actually is a smaller percentage than it was of what the absolute stiffness is here. And again, all the commercial systems statistically overlap with each other, but we do see some general mean or median differences from the grand median. Starting to tease this part as a function of then focal depth, which I've been alluding to. What you're seeing here is in either pairs or triplets for a given system, how much variability was seen in a given phantom as a function of focal depth. So the left 2 points are at depths of 3 and 7 centimeters for one system. The next 3 points were at 3, 4.5, and 7, and it repeats across the plot at 3, 4.5, and 7 for different systems. What you can see is that there's definitely a downward bias in the estimated shear wave speed as a function of depth. That was very repeatable through different systems, though the absolute location of the speeds reconstructed with each system varied a bit. Again, looking now in aggregate across all the systems as now a function of focal depth, you could see approximately a 3% change with all the systems combined. Again, there's large boxes associated with all the different other variability across the systems, but you still could see this apparent trend. The stiff phantoms also showed the same trend. It was actually a little bit more exaggerated in terms of percentage here. And the conclusion from the phase 1 study was that the focal depth bias that we were seeing was actually a bit confounded by the fact that we were doing phantom-based measurements. One of the confounders is actually the experimental protocol, where coupling the transducer to the flat surface of a phantom required a water path, which actually led to some geometric distortion of the tracking beams and led to some of that bias. Some controlled studies done afterward were able to show that we could reduce some of that focal depth bias but not get rid of it completely, so it remained on the radar as a potential confounder. So the takeaway from the phase 1 study is that most of our systems were agreeing to within plus or minus 5% of a grand median that we were looking at there. And then we wanted to up the ante and say, well, let's move to a more realistic tissue mimicking material, which would be one that is viscoelastic. And there had been literature that had already been alluding to the fact that a viscous model was more appropriate for tissue, both in MRE and different ultrasonic modalities. And we wanted to see how incorporation of viscous materials into these calibrated experiments would affect our conclusions. Just to demonstrate here some of the differences between shear wave speed reconstructions and viscous media, what I'm showing in the animation here is a displacement field propagating away from an excitation in one of our tissue mimicking phantoms that's viscoelastic. And the plot on the right is a little bit different than what I've been showing, but it's showing you that same arrival time and spatial trajectory, where time right now is on the x-axis and spatial position is on the y-axis. So the excitation starts in the upper left corner, and as you can see, kind of that trajectory that the line is fitting down and to the right, that is the slope of that line is indicative of the speed, using the same sort of arrival time metrics that we mentioned before. If I look at, instead of displacement, if I look at velocity, which is just the first order time derivative of the displacement field, you would get the bottom plot. And I don't want to highlight any of the real minutiae of this other than looking at what the projection through space and time looks like. And I think that you can notice in the bottom right figure that you see a different slope to the line. So these are the same exact data, except when there's viscosity in play, looking at a velocity versus a displacement profile actually leads to a different reconstructed shear wave speed. So this is the foundation for the concern that this is a confounder of what we might be looking at. We know from early data provided by some of the manufacturers, this is showing FibroScan, Siemens, and some supersonic Imagine data. We asked them to calibrate some of the frequency content of their shear waves. Again, without detailing too much of the specifics of the different scanners, what I just wanted to highlight is the fact that different transducers in different systems operate at different frequencies. So FibroScan, which again is not a radiation force-based system but uses kind of a mechanical punch at the skin surface to generate shear waves, those tend to be extremely narrow band systems at a relatively low frequency, so ranging from 40 to 60 hertz. whereas the radiation force systems, with the two representative ones here, are ranging sometimes between 200 to 300 hertz, going all the way down to almost 60 hertz also on their lower end. So we know we have a range of frequencies being represented by these systems. What we did for the phase 2 study was we created 3 new tissue mimicking phantoms, A, B, and C, as shown in this plot, that had different degrees of stiffness and viscosity. And we deemed them to be tissue-like by comparing it with some published data that we had looking at healthy and fibrotic patients in the NAFLD population. So these are fatty liver disease patients. And the scatter plot is showing people who have no to mild disease in the white dots versus more advanced disease in the yellow. And we were able to reasonably fabricate 3 phantoms that captured some of that stiffness and viscous response. A is being the softest and least viscous, C is being the stiffer and slightly more viscous. Okay, the next plot is just showing a wealth of data that no specific box should be looked at, but what I'm showing here is in aggregate across all the different systems, which are shown in different letters, how the systems performed in measuring in the different phantoms, so A being the top row, B being the middle row, and C being the bottom row. And as you remember, focal depth was one of our concerns, so looking at the shallowest to the left to the deepest to the right foci. And what you could see in the dashed orange lines are the grand median for each phantom and focal depth combination, and then each box is showing the representative distribution of reconstructed shear wave speed values from a given system. If a system recorded Young's modulus or shear modulus instead of shear wave speed, all of these values were converted to shear wave speed using the relationship that I presented earlier. What I am going to show then is a zoom in of one of these configurations. So this is showing that B phantom, the one in the middle, at the 4.5 centimeter depth. And what you can see here in a more zoomed in detail is just how much systems would deviate from the grand median of the system. So again, the orange dashed line is that grand median of all these data, and what you can see is that there is a bias between some of the systems. Some of these actually have very tight distributions, so they are statistically different from others. You could also see that there's differences in the variance of the measurements that each reports. And these measurements were taken over 10 replicates in each phantom. So the error bars are giving you kind of a distribution of measurements in these viscoelastic phantoms across those 10. So something definitely measurable between the different systems. One of our earlier assumptions that we also wanted to test was how a given system that was deployed at different sites compared to itself. So in this case I'm showing a single system, so a given manufacturer with the same probe type and software version number that was at 3 different locations. How did it perform at the same focal depth? And you're seeing on the left the A phantom, the middle the B phantom, and the right the C phantom, with again the 3 things representing the different sites. And what you'll notice is that for certain phantoms there's definitely statistically different reconstructed shear wave speeds from the same system at different sites. So it's another degree of freedom that we needed to investigate, and it also helped further motivate why there might need to be some testing protocols for quality assurance to make sure that a system remains calibrated over time at a given site. This is simply showing the ANCOVA from the phase 2 study. Notice that the primary degrees of freedom in bold here, again, system, site, and focal depth now all are sharing some of the burden for variability, but system now is taking over as a slightly more dominant. Focal depth is actually no longer the primary confounder that we thought it was from the phase 1, taking into account the viscoelastic media. I wanted to quickly touch on another non-ultrasonic modality that has traction in the literature for the same purpose, and that also we're trying to, through QIBA, compare to, which is magnetic resonance elastography. Unlike the ultrasonic modalities, instead of using something like acoustic radiation force, MRE actually uses an external vibration source to create shear waves within a material, and then they can reconstruct the resultant equivalent shear wave speed by looking at those wavefronts propagate. This is showing just some experimental vibrating wavefront data from these same tissue mimicking phantoms that I was just presenting in the phase 2 study. I bring your attention to two specific frequencies that they were using for their vibration. 60 hertz is what MRE uses clinically. It's also close to what the FibroScan system is. Most of our ultrasonic radiation force systems are actually closer to the 140 hertz that we have. So I just want to point out that there's two different frequencies in the plots I'm going to show next that you should really hone in on. One where MRE tends to work and one where the radiation force systems are. What the next plot here is showing is in the same phase 2 phantoms, A, B, and C, which are each shown in aggregate of all the ultrasound systems in the violin plots. What I'm showing you then in the overlaying dots are the MRE reconstructed shear wave speed values at frequencies ranging from 60 to 200 hertz. So remember how we said that in viscoelastic media we expect that we have dependence in the reconstructed speed on the frequency content of the shear wave. That means that we expect an upward trend with increasing frequency, and we see that very clearly in the MRE data. The two different colored arrows there, the pink and the cyan, pink is showing again what a clinical MRE system would measure, or potentially the frequency more close to what a FibroScan would measure. 140 is closer kind of to the centroid of each of the violin distributions of the ultrasound systems, and you can see how there is that upward bias between the 60 and the 140 hertz. So starting to touch on what the QIBA profile is trying to achieve now to ensure some better standardization in the community. Right now the QIBA profile from a technical perspective, and all of this is still a work in progress, so this is not set in stone yet, though there will be soon a public version of the profile available for comments, is that all acoustic output for these systems remain within FDA limits. That's primarily on the acoustic radiation force side. And we're actually going to impose the agreement between the ultrasound systems and MRE at 140 hertz, which right now empirically was one of the best matches we had from the existing systems, with a target corridor of plus or minus 5% on the reconstructed shear wave speed. The hope would be to do comparisons for quality assurance pre-delivery before a system would go to an institution, after installation, and then some regular quality assurance after installation. Some of these tissue mimicking phantoms can have temperature dependencies, so there would be some corridor of temperature to be measured in. And given some of the variety in how the metrics are reported on different systems, there is a recommendation to report in shear wave speed, which again using the earlier conversions should be achievable. This is just showing from the profile, the draft version, the general workflow of all the different primary blocks to making a shear wave speed estimate and how that could be correlated to liver fibrosis grading. What we're really looking at right now are all the different imagers at a given institution who might be performing this, and making sure that there's aspects of the profile in place that guide the actual data acquisition, and do that in parallel with what kind of the technical compliance would be, which would get more at the accuracy and variability of a measurement in a calibrated material. From the clinical perspective right now, the primary indication that the protocol is focusing on is liver fibrosis. There are a variety of locations where one could image the liver, and the intercostal space to target the upper right liver lobe has been what has been recommended. That has some traction because that is typically where the liver biopsy is performed, and so it will allow for a little bit more of a one-to-one comparison with the tissue being biopsied and reviewed by a pathologist. There's been some reported dependence on eating, and primarily blood flow potentially to the liver after eating, so they do recommend at least a 4-hour fasting window. Patient position and suspension of tidal respiration is recommended here, again for consistency of how the liver is positioned and what state it's in relative to the normal physiology. A general recommendation to optimize the B-mode image quality when making measurements, staying away from internal structures and the liver capsule. So staying away from bile ducts, blood vessels, at least 2 centimeters away from the capsule is recommended. Some of these things, of course, are more challenging depending on the body habitus of the person being imaged, but they are recommendations to try to achieve consistency. And right now the recommendation is to look at the median of 10 independent measurements taken from the same location. So the same acoustic window and the same relative position to any structural landmarks you might have. As I alluded to before, we have also in parallel created some digital phantom data to allow people to test reconstruction algorithms. This is for both industry and also in the research setting. We've done this both for elastic materials with different focal configurations for the radiation force that I've listed here and different elastic material properties. We've also expanded that to viscoelastic media to match the phase 2 phantoms. And again, this is really going after, is there any algorithmic difference to how people are doing the speed reconstructions in known ground truth type digital phantom data. Just to impress upon people how much variety you might see in shear wave speed that's reconstructed as a function of frequency. For the 3 different phantoms that were used in the phase 2 study, the plot on the right is showing how the discrete reconstructed shear wave speed at a given frequency changes over a range of 0 to a little bit over 500 here. And what you could see is that if I looked at 140 hertz, which was that comparative discrete frequency with MRE, what the phase velocities for the 3 phantoms would be. So for given imaging systems that might have a bandwidth that could range from, let's say, 100 to 300 hertz, if you're looking at the slope of each of those colored lines, that's showing you what gradient and speed you could potentially be seeing if you don't control for potentially honing in on a more discrete phase velocity estimate. So the hope is that if systems vary right now in a function of this frequency dependence and are able to hone in a little better, we could actually tighten up some of those distributions a little better. All of the data for the digital phantom studies, both the code used to generate a lot of it and the data itself, is hosted for free online. There's actually a GitHub group associated with a lot of the setup scripts to run these simulations, both using Abacus and LSDyna. That's freely available for people to download. The digital phantom data itself is being hosted on the quantitative imaging data warehouse that the RSNA sponsors, and we have a group up there, the Ultrasound Shear Wave Speed Digital Phantom Group. Again, all of those data can be downloaded. They're easily accessible in an environment like MATLAB, or can be read into Python or even R for analysis. So wrapping up here with a few conclusions before we have time for a few questions. Current systems right now tend to estimate shear wave speed using time-of-flight algorithms, again with a lot of assumptions about homogeneity and tissue elasticity. Our phase 1 study that looked at elastic phantoms has shown in general good agreement between the systems. We did see some differences with focal depth between different systems, which we think we honed in on a bit due to the experimental setup. We know that viscoelastic media are definitely more challenging to characterize because of their frequency dependence. We've shown that system and site variability could actually be equal confounders here right now. We actually have remarkably good agreement, I think, with all of the aggregate system data with MRE as shown in that violin plot. And taking all of these data into account, we have a first draft of that QIBA profile that's soon going to be ready for public comment. And we've also made available some digital phantom data for people to use in the research setting. So all of the work that's been presented so far in this webinar is actually the product of a very large QIBA group. I just wanted to give specific mention to some of the chairs and co-chairs of the different subcommittees of the shear wave speed group: Tim Hall, Brian Guerra, Andy Milkowski, Keith Weir, Manish Dayani up at MGH has helped a lot. Some folks here internally at Duke who I've been working very closely with, collaborators at the Mayo Clinic who've been very involved, and a lot of support from some external funding to help this. I've also included here just some general references. This is by far not a comprehensive list, but if you're looking for some of the more recent society guidelines, overview of the basic science involved here, and some overview papers of the phantom studies to date, as some of those are in the literature. And I'd be happy now to take any questions. So I have one question here. And the question is, given the dependence of shear wave speed estimates on frequency content, should manufacturers report some metric of the wave's frequency content with every shear wave speed measurement? So that's a great question, and it's one that actually the committee has gone back and forth on multiple times. The consideration that was one of the more dominant things was how the end user, being the clinician, would interpret what is presented by a given system. So one of the challenges is that to fully appreciate why someone would be reported with the frequency content would require them to understand how to then interpret that in the context of a system that would report a different frequency. That was then the motivation for trying to tie all of the systems to a common frequency that they should all have, which was the 140 hertz that an MRE system could measure. And MRE was chosen as a good comparative modality because it's such a narrow band, discrete frequency that it hones in and is not affected by that slope or gradient of speeds at adjacent frequency bands. And luckily the MRE community has been very collaborative in this regard. Plus it would also help down the road clinically that an MRE system should hopefully agree with an ultrasound elasticity system, though right now, as I mentioned, the MRE systems measure closer to 60 hertz, whereas the ultrasound systems are up at a higher 140 hertz. Okay, we have another question that's come in. A question came in about why of a median of 10 measurements instead of a mean of 10 measurements. That's another great question. Median was chosen at first historically in the literature. There was a lot of traction in the literature from systems such as the FibroScan, which actually made a recommendation of median. The main reason that I think that the community as a whole has stayed with that recommendation is that it is not uncommon to have some spurious measurements that clearly do not fall within kind of a normal distribution of variance. And by using the median metric, we're able to be able to de-emphasize the influence of some of those outliers and really converge more on what we think is a accurate representation of the distribution of variability and not a skew with that. That being said, the number of measurements being 10 and the use of median is not set in stone, and again, QIBA profiles are meant to evolve with time, and as the systems get more robust and tighter in agreement, there might be opportunity to actually drop the number of recommended measurements. Okay, a few more questions are coming in. What is the reason for performing sampling in the same area when we're studying a diffuse but not uniform disease? Another great question. So if someone were to add a confounder right now of biological variability of the heterogeneity of the disease on top of the current variability that we're trying to overcome, we know that we would expect some degree of change just with spatial distribution. And right now, the emphasis has been put on trying to get the most representative metric at a given location rather than trying to get an overall reconstruction for the entire liver. This is a bit different than the MRE data. As the pictures I show alluded to, they actually get a wave field that encompasses most of the organ, and they probably get a more overall global measure of stiffness than the ultrasonic systems, which have a much tighter region of interest. I think that if you are looking for characterizing more of the heterogeneity of stiffness across the liver, probably the current recommendation would lean more towards taking 10 measurements at a given location and then doing that at the disparate locations spatially throughout the liver to build up that map so that you have higher confidence in a reported speed at a given location. Okay, a bunch of other questions have come in. I'll try my best to get to all of these. How is the performance of these systems when imaging inclusions and heterogeneity? Another great question, and exactly not what most of them are designed to do right off the bat. At least the point measurement systems. So the 2D shear wave speed imaging systems are actually specifically trying to look at delineating structures with contrast. It's more commonly been applied to in the breast than in the liver, but could be done in the liver. I'm going to defer that to say right now that's an active research question. We have not, as a group through QIBA, tried to hone in on what the accuracy and variability is as a function of pixel size or region of interest. There is a decent amount of literature that has started to come out that has specifically looked at how the confounders of shear wave reflections at structural boundaries influence things, using different filtering schemes to specifically remove the spurious artifact components. But right now I'd say that's an active source of research more than something that's been standardized for clinical use. Another question has come in. So there's a question about the frequency that's being referred to, the 60 versus the 140 hertz. Is that the shear wave repetition frequency or the ultrasound interrogation pulse? What the different spectral values I quoted are is effectively the frequency content of the resulting shear wave. So in MRE data, they actually externally vibrate with a continuous wave source that vibrates at 60 hertz, and so the waves that are generated in the liver are temporally locked in at that 60 hertz rate. The ultrasound systems, they generate a more impulsive excitation to generate the shear waves, and so they're considered to be more broadband, so they have more of a range of frequency contents, and the 140 hertz would be the more energetic band in those resultant shear waves. So it's really reflecting the morphology of the resultant shear wave rather than any sort of repetition frequency or something like that. Another question that has come in is QIBA considering releasing recommendations on ways to avoid biological confounders. That is an active part of the document. There is a lot of very recent literature where clinicians have been looking at that. As I alluded to in the clinical part of the profile, there are recommendations in fasting for at least 4 hours, depth of respiratory suppression for doing measurements, patient orientation. I think that there's a lot of opportunity to really delineate the other clinical confounders more. And active areas of research, and I think that the first version of the QIBA profile will have some of these included, and future versions will be able to build on that a lot more. Another question here is, does body habitus such as high BMI versus low BMI affect shear wave speed measurements in the liver? Does the overlying soft tissue affect the measurement? Another great question. Right now, BMI is one of the factors that typically trends with the disease state, so it's a little tricky sometimes to delineate this. We do know in the literature that shear wave speeds can be reconstructed in people as high as BMIs in the 60s have been reported. No studies that I have seen have actually correlated BMI directly with that. We do know some systems do not work as well in ascites, so for overlying tissues, things that require the surface punch like the FibroScan have a bit more challenge going through ascites because shear waves don't couple through the fluids. Radiation force systems do not have as much of that challenge, but all of the systems will be challenged by potentially lots of different heterogeneous layers of soft tissues, specifically subcutaneous fat and the sort. Those things will degrade image quality, and that makes the tracking of the shear waves more complicated, and that's why one of the recommendations for optimizing success for shear wave measurements is actually to get the best B-mode image possible. That's the best qualitative sign that you should get the highest likelihood good shear wave data to reconstruct. So there was a question here about the choice of reporting shear wave speed in meters per second versus what is also a very common metric in the literature, which is kilopascals. As I've alluded to, and as the person asking the question has, EchoSense had a lead in the literature on this and has established some of the protocols that have been adopted. Meters per second was chosen I think by the QIBA group because that is what a lot of the underlying radiation force systems were actually directly reconstructing, and then Young's modulus was typically being reconstructed from that speed. That doesn't necessarily mean that one or the other is quote-unquote better, except for the fact that there is not a linear relationship between kPa and meters per second. So the quadratic dependence of the speed can actually expand the dynamic range of the measurements related to fibrosis relative to the stiffness, and that was by some seen as an advantageous metric. Okay, I maybe have time to squeeze in one more question, so I'm going to try to quickly pick one out from a very long list. There's a question here if physical rheological techniques could be used to get the exact stiffness of the phantoms instead of MRE. Would that be more accurate? Another great question, something QIBA considered early on. The challenge with a lot of the rheological systems that were investigated in early generation studies was actually limitations due to the fact that they worked at very low frequencies relative to the higher frequencies of the radiation force systems, and some discrepancies that were very amplified in those low frequency modes. So ideally, yes, we'd be able to have kind of an on-the-bench standard, but something that we're working towards. So I think we're out of time right now. I thank everyone for their attention. I hope everyone found this to be a productive webinar.
And I want to thank you very much, Dr. Palmeri, and our thanks to all of you who participated today in this webinar. Everyone, please remember to complete the post-test and the activity evaluation. We hope you enjoyed this presentation and will join us again for future webinars. So long, everyone. Enjoy the rest of your day.